Good morning. This is a recording of the longer version of the content that I presented last week, March 10th in Paris at the MPLS SDN Conference 2016. So, segment routing, an update, deployment experience, and new technology, new advanced use case. We are deployed. So, as we had said in 2015 at the conference, we were seeing commitment for deployment of segment routing in calendar year 2015 across all the different markets on which we were working, the web market, the service provider, core edge, but as well, and very important, the large-scale aggregation and metro, the large enterprise. And across these different markets, web service provider, large enterprise, we have seen design commitments across data center, WAN, and the large-scale aggregation, the metro. So we have seen our first deployment in 2015, and since the beginning of 2016, we are only in March, but we see really a big start, a very strong start with many new deployments. So very exciting on that side. The scope of the presentation at Paris was really to give a review of advanced use case and the related new technologies. It was very important to show the reality of this, so all the demonstrations were available at the booth, and there will be also companion to this video recording that will be posted on the segmentrouting.net website. And what we wanted to highlight as well is that we take a lot of care to maintain a detailed segment routing tutorial that is available publicly on that URL on the segmentrouting.net website once again. So, first use case, inter-domain policy at scale. So, we consider two data centers, A1 on the left, B2 on the right. We consider two metros that interconnect them to the inner core represented in black here. We're going to walk you through a typical design. So here, certainly we would advise an homogeneous SRGB for simplicity across the inter-domain design. In this example, I'm going to take a small one, 16,000 to 24,001, just to show the scale of it. Obviously, if you want to use a bigger range, like 64,000 global labels to cover your design, you can do it. This is just a specific example to see again the power, the scaling of the solution and the application to this design. So this small range, I'm going to allocate it in sub-range to each of the domain. In the core, I'm going to use a 16,000 range. For example, the aggregation router number 1 is assigned a global label 16,001. The LSR in the middle is 16,003. And the rightmost border router between the WAN and the metro is 16,002. So the 16,000 range is the black core domain. Then I give the 17,000 range for the metro A, and there the DCI 1 is 17,001, the LSR is 17,002. Then I give the 8,000 range to the metro B, and I give the global label 18,002 to that LSR, 18,001 to that DCI here. Then I allocate the 20,000 to 24,000 range to any data center in my multi-domain design. You see it appears on the left and right. And obviously, if you have, let's say, overall a scale of 30,000 nodes, you don't need to do this. You could use, for example, 40,000 global labels and make sure that every of your domain have an allocated unique range. However, if you would like to scale to millions and millions, and we have such a design on which we are working, where we are designing very large-scale data centers and inter-data center for tens of millions of physical endpoints, someone could ask, but how can you do it? Because you are limited by at most 1 million MPLS labels. How can you do it? And this is basically what I want to explain, is that we can do it because we're going to reuse where we need the same global label. And so as we go through the design, we'll see how this works. But let's note at this point in time that if I am in the left data center, 20,001 uniquely identify the leftmost VPE. 20,002 uniquely identifies the specific top of rack. 20,003 uniquely identified that spine. And so the concept of segment routing in that domain is completely applicable. In the rightmost domain, again, independently in that domain, these global labels uniquely and without any confusion identify a specific VPE for 20,001, 20,002 is that TOR, etc. It's interdomain wise that we will see how we can again have a unique identification of a single node. Now let's review the routing on a per domain basis. Inside the metro left, metro right, and the core, we are going to use independent instances of ISIS OSPF with the segment routing extension. For example, an instance 1 in the core, an instance 2 in the metro A, an instance 3 in the metro B on the right. This is technology that is available for us since June 2014 in terms of shipping release, FCS release, June 2014, almost 2 years. There's been numerous presentations on this. It's deployed. For example, a year or two ago, Stefan and Bruno reported on the testing on this. Also the interworking, the interoperability with other vendors has been reported, etc. And the benefits of the deployments of the ISIS OSPF protocol with the segment routing extensions have been also demonstrated at previous conference, specifically the incremental deployment and the seamless interworking with LDP. So very easy to get to this point of the design. Now, what do we do in the data centers? In the data centers, and here we show a typical structure for a data center with an unfolded cloth structure where you have the spine, and then you have, basically because it has been unfolded, the left a set of leaf hanging from the spine, another set of leaf hanging from the spine, then the TOR hanging off the leaf. Here it's the border routers hanging off these leaves, so these are the DCIs, and then we have the VPEs connected to the TOR. And so this type of arrangement, an unfolded cloth, typically is run with a BGP-based design. And here it's really straightforward. Once again, like for ISIS OSPF, simple straightforward extension to BGP to implement the concept of segment routing with a BGP routing protocol. So this is what we assume here in the data center. And once again, this is real. If we look at the Cisco case, there are two parts of the portfolio that already allow you to do this. Either the Nexus hardware with the XC, the NX OS, that's a mistake on this slide, the NX OS software, or the NCS 5K with the XR software. So you have two options to build such a data center with the BGP segment routing. So let's continue. Now we look at the interdomain routing. From an interdomain routing, we at this point are going to assume that there is no BGP interdomain routing. So these different islands, domains, are completely disconnected from each other. The only thing we do is that from the WAN to the metro, we redistribute the aggregation routes. So basically these border routers between the WAN and the metro are redistributed inside each of the metro. And the metro itself redistribute these WAN aggregation devices to the data center. So it means that wherever you are in a multi-domain network, you can reach AG1 with 16,001, which is a global label, globally unique in the interdomain network, and you can reach AG2 16,002. But from a upside, so from the data center to the metro or from the metro to the WAN, we redistribute nothing. So it means that fundamentally at this point of the design, we do not know how VPE1 in the left DC can reach VPE2 in the right DC. This is what we're going to explain step by step through this design. So let's introduce the segment routing PCE. The segment routing PCE is made of two blocks. The first block is the multi-domain topology, which is collected in real-time manner from each of the different domains via BGP-LS. Then we have a compute block, and this is basically where we put all of our research over the last 3 years since we started the segment routing project. And so this is where we have, let's say, invented native segment routing algorithm for doing traffic engineering computation, and so they're implemented in that compute block. Next step, we look at the service provisioning. So we're talking about layer 3 VPN, layer 2 VPN, etc. So here it's really classic. You have a VPE2 on the right, it's connected to a certain VPN tenant. He advertises a VPN route with the next stop himself and a certain VPN label. The BGP route reflector for that service plane is reflecting, and if VPE1 is part of that service plane, he will receive the route. When he receives the route, the big question is, well, VPE1 doesn't know where VPE2 is, and so how can we solve this? And here is now we're going to explain how we glue the interdomain picture together. And the solution for this is called segment routing on-demand next stop. So segment routing on-demand next stop, ODN for short, works this way. When VPE1 receives the BGP route and he sees that the next stop is something he doesn't know because within this data center VPE2 is not known, and we've seen that all of the domains are independent from each other, are isolated from each other. So VPE1 doesn't know that next stop. And here is where the on-demand segment routing next stop kicks in. It's a functionality of the router, and when he sees he doesn't have a next stop, he basically on-demand send a PSEP request to the segment routing PC and say, hey, where is VPE2? But the segment routing PC we've seen before, he has a view of the entire multi-topology, multi-domain network. So he is able to see where VPE2. Then he has the natively developed segment routing based algorithms, and he compute a path through the multi-domain topology. And it's very easy. From a human being viewpoint, we know what will be the path. It's basically to take a first segment hop to 16,002 here, which is the furthest aggregation router that we can reach from VPE1 on the path to VPE2. Then we will take a segment up to the DCI between Metro B and the rightmost data center, at which point we are in the context of that specific target data center, and in that context 20,001 is completely relevant and unique. This is VPE2. So the segment routing PC computes the same, and he replies to VPE1, hey, your path to VPE2 is 16,002, 18,001, 20,001. VPE1 installs this in his data plane, and is then going to install the VPN route on that segment routing policy. So we see that the on-demand resolution of the next stop is done by segment routing. It involves the insertion in the data plane of what we call a segment routing policy. This is basically a list of segments that leads you to somewhere with some SLA characteristic, and then the VPN routes are immediately installed with a recursion on that policy. When we started this design, we basically said that this first design is about interdomain at scale with policy. Where is the policy? So this is basically the point now of this slide. Let's now consider that the VPE2, when he advertised the VPN routes, that VPN routes needs to have a certain SLA for its return traffic, for the traffic that will come to that destination behind VPE2. And so this is accomplished by putting an external community to the BGP route that says, hey, that route, for example, needs a low latency path. The BGP route reflector reflects, VPE1 receives it, and now the ODN feature kicks in on VPE1 for two reasons. It doesn't know VPE2, and it doesn't know VPE2 with a low latency path. He asks on demand the VPE2 that question to the segment routing PC, and the segment routing PC then use really these native segment routing based algorithm to compute a path to VPE2 on the multi-domain topology that meets the SLA request low latency. As an illustration, it could be that we take a first hop at a specific entry point to the WAN, then we take a hop through a specific border router of the WAN in order to take the low latency path, maybe not the lowest cost, but the lowest latency, and we exit at a specific point of the WAN. From there, typically, there's no latency differentiation in the metro and the data center, and the rest of the path to VP2 is the same as before, a hop at the DCI and then a hop at the VP2 where we need to go. And here is how we offer interdomain reachability with SLA, and we say at scale and simplicity. So let's review again. Why is it at scale? Because it's very well known in this large-scale aggregation that each of the access nodes, if we talk about a metro aggregation, a mobile aggregation, or any of the VP, if we talk about inter-data center communication, each of these endpoints need to talk to very few other endpoints. So although you have endpoints that scales in the tens of thousands, hundreds of thousands, millions for some of the large-scale data center we are working on, the square, if you would give connectivity from everybody to everybody, that would be really bad from a scale viewpoint. And as we know that they talk to very few other endpoints, it's much more scalable to basically request them on demand. So when VP1 learns that he would need to have a connectivity to VP2, he learns that reachability on demand. So that's where we get the scale. Why do we say that we have an interdomain solution? It's obvious. We unite, we connect endpoints from different domains. Why do we say with SLA? It's because we've seen through these two examples that when the VPN route, either for layer 3 VPN or for layer 2 VPN, arrive with these external communities, the external community is like an SLA contract. And the VP1 here who receives it just detects that there is an SLA contract that he needs to commit on the reachability to the destination. And so he basically asks the segment routing PC how he can do it, because himself he cannot compute it because it's an interdomain problem, and he only sees what is available in terms of topology in his local domain data center left. Why do we say with simplicity? Because here everything is automated. The only thing you need to do is to tag the VPN routes with the SLA contract that they need to receive. The rest is completely automated. When VP1 receives the external community marking, he knows that there is an SLA contract associated to it. He on demand, so it means automated, as the segment routing PC. The segment routing PC automatically retrieves in real time all the topologies of each of the domain. He has a set of specifically designed segment routing algorithm to compute these SLA contracts on the multi-domain topology. He computes a solution and he automatically replies to VP1. If later on there would be a change in the topology somewhere and the path would need to be changed, the segment routing PC would automatically detect the change, recompute, and reupdate the VP1. So there's no need to have any tuning, configuration, or whatever. But furthermore, if we continue the path, when VP1 receives the list of segments, so what we call the segment routing policy, VP1 installs it in its data plane, and he installs directly the BGP destination, the VPN destination, the service destination, directly recursing on that segment routing policy. It also means that you do not need to configure any classification, any steering policy, any, let's say, policy-based routing, which is extremely difficult to maintain and expensive from an operation viewpoint, and also leading to mistakes over time when you basically have to maintain all of these things all around your network. Here, the steering is also automated. But furthermore, because the BGP, the VPN routes, the service routes are directly installed on the segment routing policy, you do not incur any type of performance degradation that would have been seen with policy-based routing steering. So all of these are basically eliminated and automated. So that's why we call for simplicity. But furthermore, note that we have achieved this by removing protocol. We have removed LDP, we have removed RSVP. Note that we have not added any per contract state anywhere. There's no midpoint state here. And note well here as well that there is no tunnel to configure because everything is automated. So that's why we have these claims, and let's continue. Now, let's look at a specific element of the design. This is, let's say, an option. We would recommend it, but it's not necessary. So what it is? But we would recommend that at any pair or tuple of border routers that achieve the same function on top of the individual, unique prefix segments, they are allocated as well an Anycast segment per pair per tuple. So let's take an example. The two DCIs between the Metro B and the rightmost data center perform the same function. They each have the individual prefix segment, 18,001 for that DCI, 18,011 for that DCI. However, they also perform a function that is equivalent between the two. They are both a DCI between Metro B and the rightmost data center. So we allocate to it a common Anycast prefix segment, 18,901. And so from the viewpoint of the attached domain, so in Metro B, 18,901 will either lead to DCI2 or DCI21, any one of the two. It's going to be interesting from a viewpoint of better ECMP and better high availability. So let's look at this in action. Let's go back to the case where VPE2 advertised a VPN route. We've had a SLA contract, so we are in the pure interdomain reachability case, and VPE1 received a VPN route. Well, on demand, it detects that it doesn't know about VPE2. So the ODN feature kicks in on the leftmost VPE, and he requests to the segment routing PC, hey, where is VPE2? And these specifically designed segment routing algorithm on the segment routing PC are going to detect the presence of the Anycast segments. And now they are going to try to encode the path, the reachability with these Anycast segments, if they are there. This is why I said it's optional. But if they are there, the algorithm will try to use it. And so it will reply to VPE1, hey, you need to take a hop to 16,902, which is the pair of aggregation routers between the one and the metro. And then you need to take a hop at 18,901, which is the pair of DCI between Metro B and the rightmost data center. And then you go to 20,001. Why is it interesting? It is interesting because now that flow will be load balancing better. It might basically go to that Act 2 or that Act 12. It can go to that DCI or that other DCI. It's a better availability as well, because if, let's say, the reply has been given at 12 o'clock today and at 3 o'clock in the afternoon suddenly the Act 2 router fail, well, fundamentally the segment routing PC will detect it, will recompute, and will update if necessary. But in this case, it would not even be necessary. And so it means that the traffic, the high availability of the traffic is much better, because when when Act 2 here goes down, well, 16902 is still there. And so from the viewpoint of the segment routing policy, which is used by VPE1, well, it's still working. Obviously, the segment routing PC will detect this and might change the path as a result of the topology change, but there has been no loss of traffic in the meantime. So it's better from a high availability viewpoint. Note as well that it is better from a control plane viewpoint, because in this example where, let's say, Act 2 goes down, fundamentally the segment routing PC will not change anything, because 16902, 18901, 20001 after the failure is still the best path to go to VPE2. So it means that the PC doesn't need to recompute, especially it doesn't need to re-update, and there's no need to change the fib at VPE1. So all the control plane of the system is preserved as well by using this Anycast. But once again, it's an option. So now everything in segment routing is about a few key objectives: simplicity, intelligence through automation, and the seamless transition. So the need to be able to deploy the technology in the existing network in a seamless manner. So it means here that we obviously interwork with a BGP interdomain routing. So this is represented in purple here, this is the classic design, and in many cases this is what exists today. The routing through the system would be that, for example, DCI2 advertise that he knows about the VP2/32 with the prefix SID 20001. This BGP route is advertised to VP1, and then the AG router here, number 2, advertise via BGP that he knows about AG2 here with the prefix SID 18001. That route is advertised, and so VP1 via the purple BGP advertising knows that basically VP2 is reachable via DCI2, DCI2 is reachable via AG2, and AG2 is reachable inside the local domain thanks to the redistribution that we had explained it earlier. So it means that the interdomain reachability in most cases will already exist that way with the purple case. So what we would propose in that case is that in ship in the night, you basically insert the segment routing PC solution that we just reviewed with ODN. Why? Because the ODN feature here is basically when you receive a VPN route, and if the next stop is when you receive a VPN route without SLA contract, he looks whether the next stop is known. And if the next stop is known thanks to the purple, let's say the existing interdomain BGP, then ODN says, well, I know about it, I'm going to use it, because the interdomain routing is known to be best effort. So if the VPN route has no SLA contract, that's fine. And so we use the existing. Now, let's assume that you deploy a new service with premium SLA attached to it. When the routes for this service will be received by VP1, this is where ODN will say, well, I know a reachability to the next stop via my existing, let's say, classic interdomain BGP. However, I know this is best effort. Here, I'm being asked to take a path to that remote next stop with an SLA contract. I cannot use the interdomain BGP route. It's best effort. So ODN kicks in and he sends a request to the segment routing PC to have the reachability to the next stop with the SLA contract. And this is how you can smoothly insert the segment routing PC, not simply, let's say, to redo in another way what you would have done with the purple, because from a business viewpoint doesn't make sense, but actually to solve problems that you were not able to solve previously, and to do it on value-added services. Then obviously over time, as that technology gets used, matured, you have qualified it, you feel safe with it, potentially at some point in time you could remove the BGP interdomain purple control plane. But this will be left to everyone to make his decision here. What is important to see is that it's really possible to do a smooth insertion and to link it to the insertion of value-added services. And so that's very interesting. Now, when we present this, it's very important to show the reality of this. And everything we talk about in this presentation in Paris and in the longer recording is either already shipping or is going to ship in calendar year 2016. So when we were doing this presentation, the notion of demonstration of everything we were talking is extremely important. And so here, on the website where you will have found this presentation, you'll see as well the video recording of the various demonstrations that we have been doing in Paris. So let's see one of these demonstrations. So it's an interdomain pseudowire. So interdomain from that left VP to that rightmost VP across all of these domains, but the service requires a path protection with disjoint primary and backup. So really what we have been doing in the architecture of this segment routing solution is that we want to decouple the optimization of the underlay from the service provisioning. So think about the service provisioning coming on VP1, programming it, for example, TI-LFA, the TI-LFA products, so the TI-LFA acquisition called now NSO, comes to VP1 and says you need to have a pseudowire to VP2 with that SLA contract, interdomain, primary backup, and the primary and the backup needs to be disjoint. Obviously, once the service orchestration has put this contract we call it that way, this contract on VP1, VP1 is not able to know how to do it. And this is where ODN feature automatically kicks in and says, well, I'm going to ask the segment routing PC. And the segment routing PC is going to compute with its, again, on purposely developed algorithm for segment routing on an interdomain basis, is going to compute two paths, primary and secondary, that are completely disjoint from an interdomain viewpoint. And these are visualized here. It then replies to the VPE1 with the two. And the VPE1, as we have seen before, the ODN feature is going to install this path, these segment routing policies into the data plane. And so automatically the ODN feature is going to install the service, the pseudo-wire, on these two segment routing policies. Obviously not on the two at the same time, but primarily on the primary path. And then if SBFD that is installed on each of those paths detects a failure end-to-end on the primary path, then ODN would put the pseudo-wire on the secondary path. So that's basically what you will see in the demonstration. This is shipping this year, this summer normally, and then let's see the other demonstration. Two disjoint interdomain pseudo-wires. Once again, the service orchestration, for example NSO, comes on VPE1 and says you need a pseudo-wire to VPE2 that needs to be disjoint to an abstract ID, let's say 7. And the service orchestration comes to VP11 and says you need a pseudo-wire to VP22, and he says as an SLA contract you need to be disjoint from an abstract ID 7. So from a service orchestration viewpoint, they don't need to care about the underlay topology, how to do the disjointness, etc. The only thing is to program the routers with the service and the SLA contract. And here it's disjointness compared to an abstract ID 7. So VPE1 and VP11 independently will have the ODN feature kick in and say, that VPE2, I don't know where it is. Furthermore, I don't know what it means to be disjoint from this 7. So because I don't know, I send to the segment routing PC. The segment routing PC then, he received the request and he glues them together to say, I have two people asking to destinations that are different from each other, but they must be disjoint. And so he computes segment routing path that end-to-end will realize the reachability that they both need, but independent from disjoint from each other. And so this is the visualization that you have here. Once again, you can see this in real action. This was the purpose of the demonstration. You can look at the recording, and this is also shipping towards this summer. Think again about the benefits again. Interdomain SLA with scale, with simplicity, no RSVP, no LDP, no midpoint states, no tunnel to configure, no PBR to configure, no PBR data plane performance tax to incur. Now, I'd like to highlight the binding seat. The binding seat is part of the segment routing architecture since day one. So 3 years ago, we were already planning the binding seat, and we've been shipping it actually for quite some time. So it's a reality. What is a binding seat? A binding seat is, if you wish, if you have an intermediate policy shown in purple that goes from AG1 to DCI2 and realize a low latency path through the one and the rightmost metro, using in order to realize it 4 segments, that policy, that segment routing policy, the headend, we always bind to it a local segment that we call the binding segment. Easy. The binding segment is the segment locally bound by the headend to its segment routing policy. It is installed in the data plane, and that value, for example here 4001, is installed as an incoming local label, and where the outgoing is to do pop and push the 4 segments realizing the policy. You can see the binding segment as the key that gets you into that policy. Every time, and this is already in the shipping code, that we install a segment routing policy, we associate to it a binding SID, and it is in the data plane. Obviously, this binding SID is reported to the segment routing PC in two different ways, either via PSEP notification or via BGPLS updates. So it means that the segment routing PC, they know about these intermediate policies. So when the leftmost VPE asks later on reachability to the rightmost VPE with an SLA contract that is low latency, the segment routing PC computes the path, but it detects, and this is the reason for not the reason, but one of the many reasons why it's very important to consider only on-purpose developed algorithm for segment routing traffic engineering, that the segment routing PC is able to detect, hey, that end-to-end policy is going to cross through the same path as the purple policy. So let's reuse it, because it will allow us to express the end-to-end policy with fewer segments. And this is what the segment routing PC does. He replies to the VPE and he says, hey, all what you need to do is basically to get to the AG1 16001, which you know, then there you get into the purple policy, and then once you get out of the purple policy, you are where you need to go. You are in the rightmost data center, and in that rightmost data center, 20001 is unique. It's VPE2. And so this is very important. It allows us to have end-to-end policies with much shorter segment lists. It's also very important from a churn isolation between domains, again for scaling our control plane. Because, for example, if, let's say, there would be a change in the topology in the WAN, the purple policy might change, but the binding segment is fixed. It will still be 4001. So although there's a change here in that domain, the segment routing PC knows, well, the purple is still the low latency path from there to there. It's still what I want. And so 4001 is still the good thing. So this is still thing, and this doesn't change. So this control plane interaction is stable, although there was a change here. The VPE1 does not need to do anything, and its FIB updates are also stable. It doesn't need to do anything. So it's very important to look at this as well in order to basically remove any unneeded churn or control plane chit-chat between the different pieces of our architecture. Now, it's very important to recognize that the segment routing PCE technology that we have designed it is fundamentally distributed. The way we have designed it is really similar to route reflectors. So this is why you can think about them as being deployed in pairs, per service and per geographies, really like route reflectors. So this is not a God box, one single in the middle of the network that does everything, and if it goes down, you lose everything. Not at all. Once again, you should think about it as a route reflector deployment. Note as well that I draw it this way for another reason. The segment routing PC functionality that we demonstrate in the demo is basically running in the XR code. So it means that the segment routing PC functionality really is like a route reflector. You can run it on the physical router as XR code, or you can run it on x86 hardware using a virtualized instance of the XR code. And so really like deployment of route reflectors, physical units, for example, your border routers in a specific POP to deal with that geography for a certain type of services, or maybe when you need to scale, you scale it out with instances on x86 hardware. Now, who can do more, can do less? All what I've explained it is in the context of inter-domain policy. But how about intra-domain policy? So let's take the case of an ISP that has a global footprint, and specifically it has a footprint in Tokyo and in Brussels. And the Tokyo routers need to send VPN routes, YY with low-cost contracts, and XX low latency. Let's assume that the IGP of that service provider is basically optimized, is metrics optimized to provide the shortest path along the lowest cost path. So it means that the IGP path to Tokyo from Brussels will please the needs of the red routes, YY, but it will not please the XX green route, which would require an SLA contract, low latency. How does it work? Well, very similar to what we've seen before. Tokyo is going to send a VPN route XX with the extended community that says low latency. Brussels receives it, and here the ODN feature kicks in. It says, ooh, I need Tokyo with low latency, and my local ISIS path is low cost, so it's not what I need. So I need to have a segment routing policy that does low latency to Tokyo. And so the ODN feature kicks in, but here, as we saw previously, the XR software running on the router contains all the algorithmic and the segment routing topology, because here it's intra-domain, to basically be able to compute himself what he needs. So here there is, if you wish, no segment routing PC, or the segment routing PC is really local. And so ODN kicks in and compute through the embedded functionality on the router the segment routing policy, which is, for example, here, do a 16002 hop to get to Moscow, and then once you're in Moscow, you know that the hop 16003 will be through Russia and will lead you on the low latency path from Brussels to Tokyo. So ODN kicks in, the segment routing PC, the segment routing PC functionality that is within XR compute locally for the router. We install in the data plane the policy 16002, 16003, and the VPN route is installed directly on that segment routing policy. So exactly the same, but applied to the intra-domain. So let's see a bit the benefits. The benefits is that, again, we have eliminated protocols. LDP is gone, RSVP is gone, there's no midpoint states. Note that at Brussels, I did not need to configure any RSVP tunnel at all. It's all automated by simply associating these SLA contracts on the BGP route. There's no PBR steering or complexity. There's no PBR performance tax from a data plane viewpoint. And also very interesting is the commonality. Whether you use a segment routing PC in the inter-domain case or you use segment routing TE in an intra-domain case, we are talking about the same code, the same functionality. Once you have understood it, you can use it in many different use cases, and it's always with the same small number of building blocks. So the prefix segments that you have in your routing protocol, and then the algorithmic to bind them to get to join that, to combine them together to realize a policy, and then the on-demand automated insertion of the BGP service routes recursing directly on these segment routing policies. So this completes the first use case, the first detailed design related to the inter-domain policy at scale. Now we look at an update on topology-independent LFA. So all the time in this project, we work very closely with service providers to focus our effort on real use case, on real needs from them. So here, it's well known that we've done a lot of work with Bruno and Stefan from Orange, and Bruno and Stefan have reported at previous conference all the analysis that they did and their testing on TI-LFA, showing the benefits. 50 millisecond protection, simple to operate and understand because it's completely automatically computed by the router's IGP process. We have it shipping ISIS and OSPF. It's 100% coverage across any topology. It's predictable. It's very important. The backup path is the post-convergence path. So from a human being, it's really simple to operate and understand for these three reasons. But then what Bruno and Stefan also help us to show is the optimality of the backup path. Why? Because in TI-LFA, the backup path is the post-convergence path. It's the one that has been planned by the planning team to carry the traffic when that failure really occurs. So it's the optimum one. And then other benefits that have been demonstrated are the incremental deployment and also the fact that it protects not only the segment routing traffic but as well the IP and the LDP traffic. So all of this has been well understood, I think, because we're shipping this already for 18 months. We shipped this in October 2014. This is deployed. So why is it that we talk again about it? It's because what we've been shipping over the last 18 months is link protection, and now we announce that we have node and SRLG protection, and that's basically completely covering the problem space, and we don't know at this stage about any missing requirement because we have the automation, we have the 100% coverage, it's optimum backup path, and we can do it for link node or SRLG protection, the smooth incremental deployment. It protects IP, LDP, and SR. So if you have any further need, let us know, but it seems pretty complete. So how does it work? Well, let's say that I am 2, and I look at a flow. Let's say that we look at a flow that goes from 1 to 5, and I am 2. And I'm going to show what I would do for the destination 5. It's very important when you consider TI-LFA that you keep in mind that what I'm going to explain is done for each individual prefix. So it's a full optimization and customization of the primary and the backup path on a per destination basis. I'm showing it here for destination 5, and it's really different from what you've seen with, let's say, ATM family protection mechanism and basically RSVPT, which was basically doing a very ATM friendly kind of behavior. So it has nothing to do with this. Here we optimize IP destination, so it's on a per destination basis. So I am 2, I look at the destination 5. I do a shortest path computation, and I find that my shortest path is via the next hop 3, and so I install in my data plane, well, incoming label 16,005, this is the prefix seed of 5. The outgoing label will be again 16,005 because I have not yet reached 5, and the outgoing interface is 3. So this is the green path. Okay, now what I do is that once I've found the primary path for 5, I look at what the operator would like to do in case the primary path would fail, and locally. So if the interface goes down. And here it's a policy. It says either the operator wants me to think that if the interface failed, well, the link failed, or maybe he wants me to think that if the link failed, well, it's the router that failed, router number 3 failed, it's a node protection, or maybe if the link failed, it's actually the SRLG of that link that failed, and maybe other links in the topology have failed as well. So here it's really the choice of the operator, and I highlighted you can make that choice on a per interface basis. You could do link protection on one, node protection on another one, SRLG protection on another one. Let's assume, for simplicity, that here it's the default. If the link fails, the operator would assume that it's actually only that link that failed, not that 3 is still alive and the SRLG is not involved. So I have found my primary path to 5, it's via 3, and I have found that, well, if that link would fail, I would need to anticipate that it is a link failure. So let me anticipate this, and it's a pre-computation. I anticipate this. So if I anticipate a failure of the link to 3, what would be my next best path? I just do the shortest path computation on the new topology, and I found that the next best path would be 26735. This is where the problem comes, because I am the only one computing this in anticipation of a future problem. The other routers, 6, 7, and 3, they will not know why I start to use that path because they are not aware about the local protection. We're talking about a sub 50 millisecond behavior. So specifically here, it would not work to simply send the packets on the backup path through 6, because from the viewpoint of 6, well, 5 would be reachable also via 2 and a loop would occur. So we need to encode the post-convergence path in a loop-free manner. because we cannot ask any help from our neighbors. They would not be aware that the failure occurred. So we encode it as a list of segments. And so here, the loop 3 manner of the post-convergence backup path is to say, I will push to 6, so the outgoing interface is 6, but I'll push an extra segment, which is 16,007, before the 16,005. So why? Because I want to go to 6, and from 6 I want to go to 7. At which point 16,005, the shortest path, is good for me. And so this is my backup path. So let's repeat. I was 2, and I first compute the primary path to 5. I find what is the outgoing interface. Once I find the outgoing interface, I detect what would be the anticipation of its failure, let's say a link failure. Then I anticipate, I visualize myself what would be the next topology if that failure occur. I compute the post-convergence path, and I encode it with segments as a loop 3 manner. I install this in my data plane as a backup path in anticipation of the failure. And so if now, in 2 hours from now, suddenly the interface number 3 fail, I would have be completely ready to use that entry and back up my traffic to 5 on the post-convergence path in an optimal manner and in a loop 3 manner. And I basically redo this for each destination individually. And so the crux of the things is the research to find out how to do this in a very fast manner on the CPU of the router. And that's what we did. We've been shipping it for 18 months, and so now we are also having node and SRG protection, and you can have a look at the demonstration. This is shipping in the summer time frame. So now questions could be, do we need many segments to encode the backup path on the post-convergence path in a loop 3 manner? And you can look at it in more detail, but these are basically a report on 9 different true ISP topologies for link protection, node protection, SRG protection, and these are the number of segments that needs to be used for the backup path. And you see that really the answer is no. I mean, most of the cases you don't need any additional segment and or 1 or 2 segment. It's very, very rare to use 3 or 4 and never more than 4. Now let's consider a new use case and a new technology that we were communicating in Paris last week. So the microloop avoidance. Microloop avoidance is a day 1 IP drawback. It's basically the nature of IP hop-by-hop routing. So if I am 1 and I consider a flow to 5 in the let's say in the original topology where I don't have that failure, the path is green. This is the best path. If the link fails, well, the path will be the blue path, because here you have a very bad metric here. So only when that link fails, you'll use that one. Unfortunately, when the failure occurs, 1 needs to change his mind. Instead of going 2, he's going to go to 8, but 8 needs to change his mind because he was going via 1 instead of 7, because that's a very bad metric here. And the same for 7 and 6. So dependence on when 1 updates his routing table for the destination 5 compared to the time of 8, 7, and 6, loops will occur, transient loops, and we are calling them microloops. They are called typically microloops. These microloops are a nature of IP hop-by-hop routing and can occur in any topology transition for link up, a link down, a metric increase, or a metric decrease. This is an illustration of the same upon the link up as we just said. So what we wanted to announce last week in Paris is that we have a complete solution for microloop avoidance with segment routing for local and remote topology change, for link up, down, and metric increase, decrease. So it's all again the outcome of lots of research and the encoding of that research as automated intelligence on the router. So we're talking about here about distributed behavior. So each router has that capability, has so in Paris. Once again, we always do this with service providers. So we did this in close cooperation with Bruno and Stéphane at Orange. And in Paris last week, Stéphane had a full 20 minutes slot in order to review that technology and all of his testing on the code. Once again, it's going to ship this year. All what you need to do to enable it is microloop avoidance segment routing. The demonstration was available, and you can have a link to the video recording of the demonstration. So what is important to highlight, I'll come back to maybe how it works after, but the benefits is the seamless deployment. There's no requirement for a full network upgrade. This is a local behavior of a router. If he's able to do it, well, he's going to eliminate the transient loops that are around him. And so you can deploy this technology one router at a time. Where you have deployed it, you have eliminated the transient loops. Where you have not yet deployed that intelligence, you might have transient loops. So it's not worse than, it's never worse than before. It's simply better where you deploy that technology. There is no protocol extension. This is a local node behavior. And so there's no interoperability testing, etc. It's really a better behavior of the router, a better way for him to update its routing table, leveraging the segment routing capability. The only thing you need are very basic prefix and adjacency segments, but we have been shipping them since June 2014, so it's almost 2 years at this time, so it's now pretty mature, it's deployed, etc. That's all what you need. Now, the high-level intuitions for how it works. So, upon an event, local, remote, link down or up, metric increase or decrease, I'm going to be, let's say I'm a router, I will need basically to recompute my next, my best path, and I need to update the RIP fib of my data plane. And here I'm going to do it in 2 stages. I'll have a new stage 1, and stage 2 is my normal, the behavior that you would have classically, for example, that you update your RIP fib with the new shortest path to your destination. So we insert a stage 1. And what is the stage 1? Well, here in stage 1, once we have computed the new best path, we basically have an algorithm that detects, ooh, that new best path to that destination is risky. Depending on when the other routers are going to update, a transient loop could occur. Well, these other destinations, they are completely risk-free. There's no possibility for a way to update the routing table between the routers in the network for loop to occur. So for the destinations that are risk-free, we update the fib classically. So if you wish, we go immediately to stage 2. But for the destinations where the best path change, the shortest path change, could be creating a transient loop, then we encode the new post-convergence path in a loop-free list of segments. This is very similar to TI-LFA, and that's the idea, is to reuse a lot of the research and technology from TI-LFA to also solve microloop avoidance. So you do this in stage 1, and then you wait a couple of seconds to make sure that anybody in the network is either in stage 1 or in stage 2 for the destination. And you do this for all destinations, obviously. So once these, let's say, 3 seconds have elapsed, then you go in stage 2. And you re-update your fib. Well, for the destination risk-free, they were already classically updated. But for the one at risk, you re-update these entries with the direct outgoing path without additional segments to encode it in a loop-free manner. And that works because at that time when you go there, when you do it, there's no longer any possibility for any loop to occur, because either at that time everybody is converging, is routing on the new best path, and so it's consistent, or they are routing on the new best path but in a loop-free manner using segments. And that's how we avoid the transient loops. That's an illustration of that technology. So let me remember how I illustrated this. So router 1 is sending a flow to 5 initially. Then this remote link is going to fail. Then the new best path will be 1 to 5. And we look at the destination 9, and we're going to see what 1, 8, 7, and 6 are going to do each for the destination. And so if I am 1, well, initially the outgoing interface was 2. Finally, the outgoing interface is 8. But it's a risky destination, because depending on when 8 updates, I could have a loop. So I do a stage 1 for that one. And I say initially I'm going to do 6, a hop to 6. Then I need to go through that link, and then I go to 9. And that's a loop 3 manner to go on the post-convergence path using segments. And that's my stage 1, where I stay, let's say, a couple of seconds. Then I'll go on my stage 2, my final, which is simply go to 8. Let's see what 8 does. Well, initially for the destination 9, the outgoing interface was 1. This is why it was risky. And finally, it will be 7, because it's the post-convergence path. But that's risky again, because there could be a loop with 7. So I first install my stage 1 new best path in a loop 3 manner using segments. And here it's the same. You go to 6, you go through the link, and then you go to 9, etc. And everybody does this. And that's how basically the transition loop is avoided. Now, the final part of my presentation was to give an update on SRv6. So once again, we always work in close cooperation with operators to develop this technology and the use case. So here, this is a short introduction, and later on at Paris, John Lady from Comcast had 20 minutes to go into this content with much more information and describe what are the use case, the real business-driven use case that are considered with this SRv6 deployment. So what is about SRv6? It's basically the applicability of the SR architecture to the pure IP data plane, to the IPv6 data plane. We are not talking here about any MPLS. So I wanted to really highlight that the SR architecture, since 3 years ago when we started, since day one, this is an IP-driven architecture, and it's very visible. We have removed LDP, we have removed RSVP being really an ATM family remnant. So all the architecture is IP-driven. Initially, obviously, the applicability to the MPLS data plane was obvious, and so what we did is we basically develop the segment routing control plane to be used with the MPLS data plane. However, when we did it to still be applicable to the IP pure data plane later on. So it's a IP-driven architecture that we have been doing. So all the control plane that you have seen for applicability up to now to the MPLS data plane is applicable to the IPv6 data plane, the SRv6 deployment context. So TI-LFA, link node, SRLG, microloop avoidance, SRTE, ODN, SRTE, PC, etc. All of this is reapplicable to SRv6. Fundamentally, what we need to do is to support in the data plane of the hardware platform the segment routing extension header. That's really the enabler, and that's what we were announcing in Paris last week, is that we had this support on the SR9K. It was shown at the demonstration booth, and once again, demonstration will be published together with this video on the segmentrouting.net website. I wanted also to attract the attention that SRv6 enjoys, like for the other segment routing technology, a smooth deployment plan. Why? Because you only need the SRv6 capability at the node inserting, removing, or updating the SRH. But any node that is not actually a segment itself, but that is purely a transit, is acting as a classic IPv6 node. So you can really achieve business-driven deployment objective, like shown by John Lady, initially by having a very focused analysis of where you need to insert the SRv6 capability. So once again, we are not talking about a day one requirement to have the capability deployed all over your network, but not at all. A lot of the analysis is about smooth insertion and deployment plan. This being said, we were reaching the conclusion for the time in Paris. There would have been other technologies, other use cases to review, but that was basically what we picked for Paris. So there were really all this interdomain traffic engineering at scale with the concept of SRPC, virtualize our hardware, operating as a RAT reflector, the fundamental idea of ODN, and the decoupling of the service layer programmation with the underlay optimization, TI-LFA, link node SRG protection, uLoop avoidance, SRv6 were the key themes of this year. So conclusion, segment routing is the fundamental architecture for modern IP network. What we want to provide is a unified fabric with policy through data center, metro, and WAN. That's our goal. We are delivering functionality never seen before, and I think we can say it because TI-LFA, link node SRG protection, uLoop avoidance are obvious proof of things that have never been achieved before. But if you look at the demonstration, at the use case we've seen in the interdomain policy at scale, this is also functionality never seen before. It's very strange, but disjoint interdomain is not seen. In reality, I don't think that this is a service that has been deployed somewhere. It would be extremely complex to build without segment routing. And then in this interdomain policy at scale, the concept of ODN, the concept of all of that automation where you don't need to configure traffic engineering tunnel, etc., is all functionality that has not seen before. In terms of another key point is the simplification, and this simplification we achieve it through automation of additional intelligence. So it's not that it's dumber, it's actually more intelligence, but we spend a lot of time in trying to make sure that this additional intelligence is automated. And also we remove protocol. It's very important to see that in the overall segment routing architecture, we have not added one single protocol. We have removed RSVP, we have removed LDP, and we have just focused on ISS, OSPF, BGP, PSEP with very lightweight, obvious extension. And that's it. The rest is basically using the Lego and combining them to deliver services. Look at TI-LFA, look at uLoop avoidance, look at segment routing interdomain policy at scale. This is not creating new building blocks. We are not introducing new, let's say, protocols or new concept in the segment routing architecture. We are simply using very basic prefix and adjacency segments and combining them to realize these services. Stefan, during his presentation in Paris, really highlighted this, and I think Bruno as well, that this is fundamental to understanding the power of segment routing, is that once you have the basic prefix segment, adjacency segments, the rest is about local behavior and creation of service. You no longer need to, let's say, do complex protocol addition, qualification, interoperability, etc. Not at all. Strong operator endorsement, we've seen it, multi-vendor consensus, and really an impressive deployment and velocity. 2015 we saw the deployment that we were expecting, but really this beginning of 2016 is really a very strong start. Many thanks for your time. I hope it was interesting. If you have any question, just don't hesitate. Send an email to us or to Chris, and any of your question, ideas, requirements are really welcome. Many thanks.